Hello everyone, this is the continuation of lecture 2, that is on basics of remote sensing. So before we proceed, we need to ask this question: can we use the digital number to identify the material? Digital numbers associated with the pixels are unique. Do they vary with space and time? So I will just try to explain one by one. So when we try to capture the images, basically we are trying to capture the reflected energy, right, or emitted energy. So here we have the sensor, and because of the ADC, analog to digital converter, these signals are getting some number, right, depending upon whether they are 2-bit or 4-bit or 6-bit. So we will have the different numbers. So this is called digital number, right. So this digital number, if you just try to understand, this is directly getting affected by the amount of radiation. If we have cloud cover here, the amount of energy which is reaching to this particular surface will be less, right. So in that case, earlier we have received, let's say, 80, but because of the cloud cover we may receive 60. Maybe again you put some gases which are not allowing this, and maybe aerosol or dust particle, maybe it will reduce to 20, right. So this 20 to 80 variation, it is just because of the atmospheric component as well as the amount of radiation which is released by the source, right. So in such situation, can we consider this that they are consistent over space and time? No, right. So this is answered. Can we use this digital number to identify the material? When they are varying with space and time, we cannot consider them as a unique property, right. So we can't use this. So can we use the digital number to identify the material? When it is not unique, we can't do that, because let's say I have put a mineral called quartz. So if it is having more radiation, right, if the irradiance is high, we will get 80, if it is low, then we will get 20. So this variation says that we can't use digital number to identify the material because they are not unique through space and time, right. So in such situation, what we do, we try to generate or we try to derive a number which is unique through space and time, right. So the radiance, now I will again explain you. Let's say this is the source and this is the sensor, this is the surface. This surface is receiving the intensity or the radiance from the sun, so we call it irradiance, right. Irradiance. The amount of energy which is getting reflected or emitted, which is reaching to our sensor, this is called radiance, right. And then what we do is we try to use this ADC, analog to digital converter, to convert this radiance to a number. So that will be a scaled number. So DN value is a scaled number, depending upon whether it is 2-bit, 4-bit or 6-bit or 8-bit, these numbers will be decided. If your sensor is 2-bit, you will have 2 to the power 2, right. If it is 8-bit, 2 to the power 8. So if it is 8-bit, you will have 0 to 255 range, because total is 256, right. So 0 to 255 is 256. So in such situation, it directly getting changed when we are changing the radiometric resolution, right. So this radiance, irradiance and this DN number, none of them can be considered as a unique property, right, because our material is located here whatever energy is coming to this, they will interact with the material composition, and then depending upon that, amount of energy will be reflected. So, this reflected energy is reaching to our sensor in the form of radiance. So, now what we have to do? We have to change this DN number to radiance and then to reflectance. Right. So, once we have this, then we can consider this is a unique. How? Again we will discuss that part, right. So, we will start with the radiance, which is L lambda. It is the radiant flux per unit solid angle leaving an extended source in a given direction per unit projected source in that direction. So, here the unit of the radiance is watt per meter square per steradian, right. So, this watt per meter square per steradian, that will be used to define our radiance. In remote sensing, radiant flux is certain wavelength leaving the projected source area A within a certain direction theta, and the solid angle are important, right. So, you can consider this is the solid angle, right, and this is the amount of energy which is reaching to the surface, and then it is getting reflected, which is coming as a radiant flux. So, here we have this watt per meter square per steradian unit, and steradian is a cone angle in which the unit is radian, or 57 degrees 17 minutes 44 seconds. So, the reflectance is defined as the ratio of radiant flux reflected from a surface to the radiant flux incident on it, and it is a unitless property, right. So, remember, reflectance is a unitless property. Now, I will try to explain this with this diagram. You have sun as source of light, this is our surface, this is the sensor, right. So, light is falling on this particular surface, getting reflected. For time being, we are ignoring the atmosphere to understand this basic concept, radiance, irradiance and reflectance. Now, the amount of energy which is coming and reaching to the surface, that is irradiance, right. This amount of energy which is reflected, that is called radiance, right. Now, here we had the DN number. We have converted the DN number to radiance using the scaling factor that is available from the space agency when you download the data. So, now assuming that you have a radiance and you also have a irradiance, because the same sensor you can put it here and then you will measure how much amount of energy which is reaching to the surface, and then the same sensor is placed here to measure how much of energy is reflected from the surface, right. So, once we have this, then we will do the ratio. So, reflectance is equal to radiance by irradiance, right. So, here we had the watt per meter square per steradian. Here also we have watt per meter square per steradian, right. The unit of radiance and irradiance, because we are using the same sensor here and here, right. So, once we have that, then reflectance will be unitless and it will range between 0 to 1. So, 1 is the higher one, 0 is the lowest one. So, the value of reflectance will always within 0 to 1. Now, coming back to our atmospheric condition and whether DN values can be used as unique value or not. Now, you will be able to understand, since the DN values and the radiance both are getting affected because of the amount of irradiance. However, when we calculate the reflectance, we are doing this ratio and we are removing the impact of irradiance, right. So, here you can see that reflectance is radiance by irradiance and it is a unitless property. So, because of this it can be considered as unique value, right. So, if I put a quartz here, if I measure it in India or US or Canada, everywhere this will get the same value it is getting in India, US or Canada. So, this reflectance will be unique value which is consistent through space and time, right. Whether you measure it today or tomorrow or maybe after 1 year in different places, the quartz should have the same reflectance value, and that is the basis of remote sensing, why we are using remote sensing. So, the transmittance is defined as the ratio of the radiant flux transmitted through a surface to the radiant flux incident to it. This is again a unitless property. Absorption of the electromagnetic radiation is the process where the energy of the incident light is taken up by the matter. So, this absorption, transmittance, reflectance, all of these are unique property, unique value which can be used to measure or identify the material, right. Now, we will try to understand these concepts: spectral reflectance, Lambertian surface, diffuse reflector. So, we will go one by one. So, let us understand the spectral reflectance. Now, if you remember that what we used to generate or what we used to calculate the reflectance, we used radiance and irradiance value, right. So, when we have reflectance, we use radiance by irradiance, right. Now, this is the general concept. The reflectance is a ratio of radiance and irradiance. But when we talk about the remote sensing data, where we have 4, 5, 6 or tens of bands, right, we have to do it wavelength wise. So, let us say first band is generated using this 400 to 500 nanometer. Second band is 500 to 600 nanometer. Third is 600 to 700 nanometer. And the fourth one is 700 to 800 nanometer. Now, if I have to calculate the reflectance, which is this one, right, what we have to do? We have to consider one pixel value, which is basically the DN value, and that we have converted to radiance. So, we have radiance value from here, right, and for irradiance we will use the same sensor to measure the irradiance in this particular wavelength only. So, now it will be reflectance of 400 to 500 nanometer is equal to radiance of 400 to 500 nanometer divided by irradiance of 400 to 500 nanometer. I hope this is clear. So, once we do that, then for this particular image we are able to generate the reflectance image. Earlier it was radiance image. Now, using this concept we have generated the reflectance image. So, the first image is available. This is reflectance R 400 to 500 nanometer. Now, for the second image again we will consider the irradiance measured in this particular wavelength, that is 500 to 600. Then we will also have one reflectance image, then next band, then next band. So, this is the reflectance calculation wavelength wise. So, with respect to wavelength we are calculating the reflectance. Now, this information we can use if we have this for the same area, all these images, then we can use these values, the reflectance value, to draw this kind of graph. Here we will have the wavelength, here we will have the reflectance. Then these values will be here, somewhere here. This is just a example. So, this kind of spectral curve we will generate for one pixel in using the reflectance value. So, this is called the spectral reflectance. Now, sometimes what happen, our remote sensing sensors are capable of generating only point information, right. So, one of the example is a spectroradiometer. So, that is capable of measuring the irradiance and radiance in different wavelengths. So, in such situation what happens, you have two columns, you have irradiance and this is radiance and this is the location. So, let us say for this particular area, in one particular point, you have used that instrument to measure the irradiance and radiance, and this wavelength. So, let us say this is 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, this is 1, right. So, here you have one value x1, x2, x3, x4, x5, x6, x7, and here you have radiance y1, y2, y3, y4, y5, y6, y7, right. Here we can write the reflectance. So, considering this is one tabular data that is being generated by the spectroradiometer. So, for this particular point, the instrument has generated irradiance and radiance information for different wavelength region, right. Now, if I have to calculate the reflectance, it will be radiance by irradiance. So, y1 divided by x1, y2 divided by x2, y3 divided by x3, y4 divided by x4, y5 divided by x5, y6 divided by x6, y7 divided by x7, right. So, if we have this kind of calculation, so basically we are trying to generate the reflectance value with respect to wavelength. So, this is called spectral reflectance. I hope this is clear. When we have satellite image, when we have tabular data which is for the point information, so in such situation how to calculate the spectral reflectance, right. Now, we will continue with this and we will go to the next topic, which is Lambertian surface. Now, the Lambertian surface is a surface which reflects equal amount of energy in all the direction. So, considering this as a Lambertian surface, so here the light which is coming from any source, it can be sun, it can be your own source of light. So, this surface will reflect equal amount of energy in all the direction, right. So, here and it is assumed that this particular surface is reflecting all the energy which is falling on it. So, this reflected energy will be 1. Remember, reflectance ranges between 0 to 1, and since we are talking about the Lambertian surface, it is reflecting equal amount of energy in all the direction, and it does not absorb, it does not transmit any amount of energy. So, in such situation, the value for the reflectance for this particular surface will be 1, right. So, if we consider, you may remember the black body concept, right. So, black body absorbs all the incoming radiation. So, in such situation what will happen? Your black body will receive zero reflectance, right. So, if I put a black body here, the property of the black body is it will absorb all the incoming radiation, right. So, once it absorb, it has to maintain the equilibrium with the surrounding. In such situation what it will do? It will emit the energy in longer wavelength region, but in the reflective domain it will have no signal. So, the reflectance for the black body will be 0 and reflectance for the Lambertian surface, that is 1, right. Similarly, if you consider emissivity, the emissivity for the black body will be 1 because that will receive the highest number, and emissivity for the Lambertian surface, that will be 0, right. So, that is very, very important when we are dealing with the remote sensing instrument. So, I hope you will see some of the instrument in future and then you will recall all these concepts. Then comes the diffused reflector. So, the diffused reflector says that when you are having the sensor here, then comes the concept of diffused reflector. So, the diffused reflector is different from the Lambertian surface because diffused reflector says it will reflect equal amount of energy in all the direction, but it will also have some amount of absorption, some amount of transmission, right. So, this diffused reflector is slightly different from the Lambertian surface. This slide is meant to explain the basic concepts of reflectance. So, here you can see sun is illuminating this particular target, right, and if the observer is here or your sensor is here, it will receive some amount of reflected energy. But if you change the position from here to here, what will happen? The amount of energy will also get changed. So, that is why it is very, very important to make sure at what angle you are doing this remote sensing. That is very, very important. This is the Lambertian surface which we talked earlier. So, this Lambertian surface reflects equal amount of energy in all the direction. That is why it does not matter whether you are here, here, here or here, you will receive same amount of energy. However, when you change this to natural surface, it will vary with position, right, because these surfaces are not smooth surface, these are rough surfaces. Coming back to the digital number that we measured earlier. So, DN value recorded by the sensors are also affected by the illumination conditions. So, here you can see the illumination condition controls the amount of reflected energy from the target. Recorded DN values are based on the received intensity and instrument capability to resolve that. During a sunny day, same pixel may have higher DN values and very low values in the cloudy condition. Therefore, it is important to convert the measured DN values to reflectance, because the reflectance can be considered as a unique value. It does not change with the space and time. Reflectance is a unique for a given material and does not get affected by the location of the measurement, right. So, once we have that, then we can consider this reflectance as unique value. So, how to convert DN to radiance value? So, that is, to convert the DN to radiance, we can use this formula. So, here the radiance is equal to the DN value multiplied by the band scale factor. This information will be provided by the space agency who has launched the satellite, and the offset will be available to you. So, for example, some of the satellites, they have this band 1, scale factor is this, offset is this. Once we have that, you can calculate the radiance, right. And in the other condition, when you have more information about your sensor, you can calculate the calibrated radiance, and here we use the L max which is the high gain, then low gain, and the Q-cal mean and Q-cal max, that is the radiometric resolution. If it is 8 bit, it will be 1 and 255 or 0 to 255. It depends upon the radiometric resolution. The Q-cal is the DN value that we have to convert to calibrated radians, right. So, using this formula you can calculate the calibrated radians. Q-cal max will be changed if the radiometric resolution of the image is different from 8 bit. So, for 8 bit this is how we calculate. Now, we have the radiance value. So, we can calculate the radiance to reflectance. Now, we can use this formula. This is RTO, this is reflectance top of the atmosphere, because the irradiance that we are going to use, that is measured at the level of the sensor, right. So, that irradiance does not have the any interaction with the atmosphere of the earth. So, in such situation we will call it reflectance top of the atmosphere. So, here we are using the pi L lambda d square, which is the earth sun distance in astronomical unit, ESUNI, that is mean solar exo-atmospheric irradiance. Remember, I told you that we are going to use the irradiance measured in the space, right. Then Z is the solar zenith angle. So, all these information will be available to you, and this earth sun distance in astronomical unit, that is given in this particular table, and the day of the measurement will be provided to you in Julian date. So, the Julian date starts from 1 and it ends with 365. Accordingly, you can select the distance value from this table. Then radiance to reflectance conversion. Then comes the mean solar exo-atmospheric irradiance. The mean solar exo-atmospheric irradiance is calculated by integrating the relative spectral response of each band and the solar irradiance over the wavelength, right. So, here ESUNI is given with this formula, and for this Aster satellite image, this ESUNI is available for each of the band that can be used to calculate the RTOA. And cos Z, that is basically solar zenith angle, and the solar zenith angle can be calculated using the solar elevation angle. In the metadata file, you will get this solar elevation angle. So, 90 degree minus solar elevation angle is the solar zenith angle. Now, this ESUNI for the Landsat product, which is from the USGS. So, you can see that all these ESUNI values are given for different bands of different sensors. Similarly, for this Aster product, this ESUNI is given. So, depending upon which satellite data you are using, accordingly you have to select the ESUNI value. Now, we will try to calculate the radiance using the hypothetical DN value. So, here we are going to use this radiance using this formula for band 4 of Landsat 7 ATM plus. Here the DN value is 216 and radiance for band 4 is given, right. And here you can calculate, and then it is coming 203.28 watt per meter square per steradian. Now, taking the other equation into the picture, the calibrated radiance, here we will use the same value and then we will try to calculate the calibrated radiance. So, here it is coming 203.54. So, there is a slight changes when you are going with the scale factor radiance calculation and when you are going for the calibrated radiance calculation. Now, once we have those values with us, then we can go with this RTOA and then we can calculate the reflectance. So, here we are going to use this 203.54 watt per meter square per steradian, and D, that is 0.99 square. ESUNI, we have referred to that particular table of Landsat 7 ATM plus, and then cos Z we have calculated using the solar zenith angle, and which is coming 0.94. So, using this, if we calculate, we are getting this 0.634. This is the reflectance value. So, this is the unique value that we talked about, right. So, with this I will end this lecture. the lecture 2, and we will continue this course with the lecture 3 in the coming summer. Thank you.